Once again, welcome to today's discussion of our chapter 5, and that is the Moivre's theorem and the Euler's formula, which is still under complex variables, column 1. Let us begin with the Moivre's theorem. And under the Moivre's theorem, we shall mainly look at stating the Moivre's theorem. We shall look at also proving the Moivre's theorem. Then we shall look at areas where the Moivre's theorem is employed. Mainly, it is employed in proving trigonometric identities and also solving roots of complex functions. Let's begin with knowing how to state the Moivre's theorem. This theorem states that for any complex number z raised to a power, that is to say, z power n is equal to r power n into cos theta plus I sin theta power n is equal to r power n into cos theta n theta plus I sin n theta. For the case where r is equal to 1, meaning that if we substitute r is equal to 1 in this expression, we shall have z power n is equal to cos n theta plus I sin n theta. Because once we substitute 1 power n, just remain 1. So we have a silent 1 here. And next is to have final expression for the Moivre's theorem. So hence the Moivre's theorem states that cos theta plus I sin theta power n is equal to cos n theta plus I sin n theta, where this n is a rational integer, and this n can be 1, it can be 2, it can be 3, it can be 4, and so on. So this is how we state the Moivre's theorem. Then next part is to look at proving the Moivre's theorem, and we shall look at how to prove it using induction method. Let us look at different steps. The first step is if we let n equal to 1, this means that cos theta plus I sin theta power 1 is equal to cos theta plus I sin theta. Once we multiply 1 with the angle, where we shall have cos theta, then plus I sin theta. Then the next step is if we take n to be equal to m, and then we make the same substitutions, we shall have for cos theta plus I sin theta power m equaling to cos m theta plus I sin m theta. And also for n is equal to m plus 1, we shall have cos theta plus I sin theta power m plus 1 will be equal to cos theta plus I sin theta power m, then times cos theta plus I sin theta power 1. Here we apply the laws of indices. If we have the same base, we add the power, so it will take us back. Then the next step is to multiply the integer m with the angle and the integer 1 with the angle. So we shall have cos m times theta plus I sin m times theta, then into cos theta times 1 plus I sin theta times 1. So we have a silent 1 here and here. Then the next step is to open the bracket, so we shall have cos m theta times cos theta, which is cos m theta cos theta, then cos m theta times I sin theta, which is I cos m theta sin theta, then I sin m theta times cos theta, which is I sin m theta cos theta, then lastly will be I sin m theta times I sin theta, which will be I squared, but remember I squared is a negative 1, so we shall have negative sin m theta sin theta. Then the next step is to correct like terms, the real parts together and the imaginary parts together. So we shall finally have real parts being cos m theta cos theta minus sin m theta sin theta plus I into cos m theta sin theta plus sin m theta cos theta. Then applying compound angles from trigonometry, we shall have that cos m theta cos theta minus sin m theta sin theta equaling to cos m theta plus theta, then plus I sin m theta plus theta. That is the part, the real part, and this is the imaginary part after applying compound angle from trigonometry. Then finally you can pull out theta since it is common. Shall have cos theta into m plus 1, then plus I sin theta into m plus 1. So we shall find that when you look at these three cases, first case where n is equal to 1, second case where n is equal to m, and the third case where n is equal to m plus 1, satisfy or for the Moivre's theorem. So meaning that since the theorem is true for n is equal to 1, which we have seen here, n is equal to m, which we have also seen here, and for n is equal to m plus 1, which we have also seen here, then it is true for any integer of n. Let's look at some examples, and as we have said that it is mainly employed in proving trigonometric identities, let's see how we can prove that cos 5 theta is equal to 16 cos power 5 theta minus 20 cos power 3 theta plus 5 cos theta. Using Moivre's theorem, whereby cos theta plus I sin theta power 5 is equal to cos 5 theta plus sin 5 theta. So here our integer is 5, and now from the proof we can consider the power for this case. From the proof that is required, we can consider the power to be 5. So the next step is cos 5 theta is equal to the real part of cos theta plus I sin theta power 5, and imaginary of cos theta plus I sin theta power 5 is equal to sin 5 theta. So here we identify the real part and the imaginary part. So we equate the real parts together and the imaginary parts together. Then the next is expanding, which is let's see how to expand cos theta plus I sin theta power 5. So expanding this one, we can easily do it by using Pascal's triangle, whereby this will be cos power 5 theta plus 5i cos power 4 theta sin theta minus 10 cos power 3 theta sin squared theta plus 10i cos squared theta sin power 3 theta plus 5 cos theta sin power 4 theta plus I sin power 5 theta. So it's simple to generate Pascal's triangle. You write 1, 1, then 1, and the next will be 1, 1 plus 1, 2. Then you write 1, then the next is 1, 1 plus 1, 3, 1 plus 2, 3, 2 plus 1, 3, then 1, then the next will be 1, 1 plus 3, 4, 3 plus 3, 6, 3 plus 1, 4, then 1, then write 1, 4 plus 1, 5, 4 plus 6, 10, 6 plus 4, 10, 4 plus 1, 5, and then lastly 1. So we shall find that since the power here is 5, so we shall stop on 5, but if there are other powers like power 6, 7, we go ahead and generate. So we shall find that these are the coefficients. So we shall have the coefficient of 1 for the first term. For the second term, coefficient is 5. Third, coefficient is 10. The fourth part, coefficient is 10. The fifth part, coefficient is 5. Then the last part, coefficient is 1. Then another thing to note is that the power of these terms, the power of cos theta keeps on reducing, and the powers of I sin theta keeps on increasing. So that's how cos theta plus I sin theta power 5 can be expanded to cos power 5 theta plus 5i cos power 4 theta sin theta minus 10 cos 3 theta sin squared theta plus 10i cos squared theta sin cube theta plus 5 cos theta sin power 4 theta plus I sin power 5 theta. Then the next step is to correct like terms, bringing real parts together and imaginary parts together. So we shall find that the real parts are cos power 5 theta minus 10 cos power 3 theta sin squared theta plus 5 cos theta sin power 4 theta plus I into 5 cos power 4 theta sin theta plus 10 cos squared theta sin cube theta plus sin power 5 theta. So therefore we can now look at equating the real parts of the left hand side at the right hand side. So therefore from what we need, cos 5 theta is mainly for real part of this expression. So we shall find that cos 5 theta will be the real part, which is cos power 5 theta minus 10 cos power 3 theta sin squared theta plus 5 cos theta sin power 4 theta. So we go back and check our proof. It is not yet correct. So since it is not yet correct, we look at what we don't, or what is not required in the proof. We have sin squared theta and sin power 4 theta. So we are going to substitute sin squared theta and sin power 4 theta. And we know that sin squared theta is the same as 1 minus cos squared theta. So where we have sin squared theta, we substitute 1 minus cos squared theta, and this will give us cos power 5 theta minus 10 cos power 3 theta into 1 minus cos squared theta plus 5 cos theta into 1 minus cos squared theta, then squared. Since this is power 4, we shall take the square of 1 minus cos squared theta. So from there we open the brackets. We shall have cos power 5 theta minus 10 cos power 3 theta plus 10 cos power 5 theta plus 5 cos theta minus 10 cos power 3 theta plus 5 cos power 5 theta. And if we correct like terms, cos power 5 theta will be added plus 10 cos power 5 theta, then plus 5 cos power 5 theta, which gives us 16 cos power 5 theta. Then minus 10 cos power 3 theta can be added on minus 10 cos power 3 theta, which gives us minus 20 cos power 3 theta. And then we add 5 cos theta. So this gives us the proof which is was asked for, meaning that cos 5 theta is equal to 16 cos power 5 theta minus 20 cos power 3 theta plus 5 cos theta. So this is how we can use this is how we can use the Moivre's theorem to prove this trigonometric identity of cos 5 theta. And let's look at example 2. We are required to prove that sin 5 theta over sin theta is equal to 16 cos power 4 theta minus 12 cos squared theta plus 1. So still the power, we can identify the power from the required proof. So meaning that we shall have to consider cos theta plus I sin theta power of 5, which is equal to cos 5 theta plus I sin 5 theta. That is the first step. Then the proceeding steps will be cos 5 theta is equal to real parts of cos theta plus I sin theta power 5, and sin 5 theta is equal to imaginary part of cos theta plus I sin theta power 5. So now we expanding cos theta plus I sin theta power 5 we still use Pascal's triangle to expand this and obtain the whole of this expression. So expanding cos theta plus I sin theta power 5, we shall get cos power 5 theta plus 5I cos power 4 theta sin theta plus 10 cos power 3 theta sin squared theta minus 10I cos squared theta sin power 3 theta plus 5 cos theta sin power 4 theta plus I sin power 5 theta. Then we go ahead and correct like terms, the real parts together and the imaginary parts together, which will be cos power 5 theta minus 10 cos cubed theta sin squared theta plus 5 cos theta sin power 4 theta plus I into 5 cos power 4 theta sin theta minus 10 cos squared theta sin squared theta sin cubed theta plus sin power 5 theta. Therefore, sin 5 theta is equal to 5 cos power 4 theta sin theta minus 10 cos squared theta sin cube theta plus sin 5 theta. So for this case, we are equating the imaginary part together, whereby the imaginary part is sin 5 theta is equal to 5 cos 4 power 4 theta sin theta minus 10 cos squared theta sin cube theta plus sin 5 power 5 theta. Now after that step, since the proof is required to be divided by 5, so we divide, since the proof is required to be divided by sin theta, so we divide by sin theta both sides. So if you divide sin theta both sides of this equation, we shall have sin 5 theta divided by sin theta is equal to 5 cos power 4 theta sin theta minus 10 cos squared theta sin power 3 theta plus sin power 5 theta divided by sin theta. So we shall reduce sin theta once. If you also reduce once here, remain sin squared theta. So also reduce once and remain with sin power 4 theta. This becomes 5 cos power 4 theta minus 10 cos squared theta sin squared theta plus sin power 4 theta. In the next step, we shall have since we shall have to substitute for sin squared theta, since in the proof we want only a cos. So we shall have 5 cos power 4 theta minus 10 cos squared theta into 1 minus cos squared theta plus 1 minus cos squared theta then squared. So from there we shall open the brackets, which becomes 5 cos power 4 theta minus 10 cos squared theta plus 10 cos power 4 theta plus 1 minus 2 cos squared theta plus cos power 4 theta. And then if we correct like terms, we shall have 5 cos power 4 theta added to 10 cos power 4 theta, and then added to cos power 4 theta, which gives us 16 cos power 4 theta. Then the next will be minus 10 cos power 2 theta minus 2 cos power 2 theta, which gives us minus 12 cos power 2 theta, then plus 1. So that will be the proof for this identity of sine phi of theta divided by sine theta. So those are the two examples on how we can use the Moivre's theorem to prove trigonometrical identities. Then exercise, you can try some of these three numbers. Use the Moivre's theorem, show that 1 cos 6 gamma is equal to cos power 6 gamma minus 15 cos power 4 gamma sine squared gamma plus 15 cos squared gamma sine power 4 gamma, then minus sine power 6 gamma. Or number 2 is tan power 3 beta is equal to 3 tan beta minus 3 tan cube beta over 1 minus tan power 2 beta. Then plus 3 is tan 5 beta is equal to 5 tan beta minus 10 tan beta plus tan 5 beta over 10 minus 3 tan squared beta plus tan 4 beta. Tan power 4 beta. So, sorry, tan 4 beta. So you try these numbers. There are 3 numbers. Try them out. Let's look at exponential form of the complex numbers. So a complex number written in polar form as z is equal to cos theta plus I sin theta can be given in exponential form as z is equal to e power I theta, where e power I theta is equal to cos theta plus I sin theta. And this is what we call Euler's formula. So writing a complex form in exponential form, it takes us to a formula, and that is what we call Euler's formula. Euler's formula is derived from the fact that e power x is equal to 1 plus x squared over 2 factorial plus x power 3 over 3 factorial plus dash dash dash. For z is equal to r into cos theta plus I sin theta, we shall find that it will be expressed as r e power I theta. Then if the complex conjugate is considered, so we shall find that where there is imaginary part, the sign is changed and it becomes z bar is equal to r into cos theta minus I sin theta, which is equal to r e power minus I theta. Let's look at some worked examples. Show that number 1 cos theta is equal to e power I theta plus e power minus I theta over 2. So we are required to prove this expression. But if you have cos theta, can be written as e power I theta plus e power minus I theta divided by 2. Then number 2, that sin theta is equal to e power I theta minus e power minus I theta divided by 2i. Let's look at the solutions. Number 1, e power I theta plus e power minus I theta divided by 2 is equal to, so we are going to substitute e power I theta, which we have seen that it is cos theta, plus I sin theta, then plus e power minus I theta is cos theta minus I sin theta. Then we divide everything by 2. So opening brackets, we shall have cos theta plus cos theta, which gives us 2 cos theta, then I sin theta minus I sin theta, which gives us 0. So we shall remain with 2 cos theta over 2, whereby 2 cancels, and we remain with a cos theta. Then Roman 3, we have Roman 2, e power I theta minus e power minus I theta over 2I. This is the same as to say cos theta plus I sin theta, then minus into cos theta minus I sin theta. We divide everything by 2I. We go ahead and remove the brackets. Cos theta minus cos theta is 0. Then we remain with I sin theta minus minus, which becomes the plus I sin theta. This becomes 2I sin theta, whereby the 2I will cancel and remain with sin theta. So, using Euler's formula, we have proved the two identities. So we can use the Euler's formula to prove these identities, as we have clearly shown these two identities down with cos theta plus sin theta. We have exercise that you can try in your free time or at home. Using Euler's formula, prove the following identities. Roman 1, sin power 3 theta is equal to 3 out of 4 sin theta minus 1 out of 3 sin 3 theta. Then Roman 2, cos power 4 theta is equal to 1 over 8 cos 4 theta plus half cos 2 theta plus 3 over 8. So these are two questions that you can try out. Thanks for watching, and our next discussion will be mainly on roots of complex numbers.